Right. So question 6. Okay, this gives us the acceleration time graph, right? And it's asking us for the velocity time graph. So how are we going to go? To go from an acceleration time graph to a velocity time graph, it's actually quite challenging to think about, right? It's much easier to think about going the other way, right? Okay, because when you go the other way, all you've got to do is you've got to look at the gradient of the velocity time graph to work out the acceleration time graph, right? Okay, so let's look at B first of all. All right, B would give us an acceleration time graph with a positive, so this has got a positive gradient, okay, and it's constant. So that would give us acceleration time graph that looks like that, right? Okay. Similarly, if we look at D, okay, this one has got a negative gradient and it's constant. So that would give us a graph that looks like that, right? Let's have a look at C. So C starts off with 0 gradient, okay, then it ends up with a negative gradient, then it ends up with 0 gradient, okay? So what would that look like? That would look like that. Okay, so you can see I've saved the best till last. Okay, if we're doing this one, then this graph's got 0 gradient, then it's got positive gradient, then it's got 0 gradient. Okay, so starts off with a 0 value for acceleration, then we end up with a positive and maximum value for acceleration, then we end up with 0 value for acceleration, right? We're just linking it to the gradient of this graph here. All right, quite challenging on that one. So the correct answer was A. Okay, if it's launched upwards with initial velocity, blah, 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 horizontal component of the velocity and the vertical component of the velocity at this later time. All right, so what this is saying is we're starting off and it's launched, okay, it's got U and it's got that angle theta there, okay. So if we have a look at the horizontal component, okay, then that is going to be so Ux is going to be U cos theta. Why? Because that's a right angle triangle. Okay, you've got the adjacent here, this is the hypotenuse, okay, this is the opposite. Okay, there we go. So it's just resolving that vector. Okay, if we're trying to find the vertical component of initial velocity, then that's Uy is going to be equal to U sine theta. All right, but it's not asking us for what's happening at the beginning, right? It's asking us for what's happening at the end. Okay, so let's just take a look. So that our horizontal component is going to be unaffected. Why? Because air resistance is 0, so the object will neither accelerate or decelerate. Okay, so at the beginning it's going to be U cos theta, and at the end it's going to be U cos theta, right? So straight away we can get rid of C and D as potential answers, right? Okay, so now we've just got to choose between these two, and hopefully you can see that if, you know, initially we start off with this velocity, at the end, okay, then we're going to end up with this velocity. Yeah, so it's going to be exactly the same magnitude, okay, as the initial vertical component of velocity, but now it's going downwards. Why? Because it's been accelerating downwards throughout its entire flight. So that's going to be minus U sine theta, which is B. Okay, projectile is moving in air at the path shown, which is the direction of the net force, okay, on at the point shown, right? So we've got to think about what forces are acting on this thing. Okay, you're going to have weight downwards, okay, and then we've also got air resistance, right? So we're worried about air resistance. If we weren't worried about air resistance, then we'd get a perfect parabola, right? But you can see from the shape that there isn't a parabola. So although it doesn't explicitly mention air resistance, you can infer that air resistance is there just by looking at the question, right? Now, air resistance is going to oppose the motion, okay? So at the beginning, when it's traveling in this direction, okay, then the air resistance is going to act opposing the motion, right? So here, air resistance is going to act along the direction of A, right? Okay, like that. Okay, so we've got to add so that's the frictional forces acting on this, or you could call that the drag forces, right? So now we've got to add these two together. You can either do the kind of top to tail method, or you can kind of imagine, that parallelogram there, okay, and that is going to be that one there. So, okay. Otherwise, as I said, you can do the top to tail. So you do that one first, and then you do that vector like that, okay, and then that's the remaining vector, which is B. All right, toy balloon on the end of a string. Free body force diagram, similar idea. We need to get our heads around, what are the forces here. So let's think it through. Okay, we're gonna have some weight for the balloon. Okay, that's not going to be a hugely long force because it's a balloon, right? We can see that it's in translational equilibrium. Okay, and that means that the sum of all the forces need to be 0, right? Okay. What other forces have we got? We're going to have like the upthrust or the buoyant force. Okay, this is clearly a helium balloon. Okay, not an air balloon. Okay, like that. We've got the air pushing on it. Okay, and the air is pushing it over to the right, so that's the force of the air. And then the final force, of course, is we've got the tension in the string here, right? Okay, so which one does that look closest to? Well, we can get rid of B straight away because B doesn't have any tension, and we can get rid of D because there isn't any upward buoyant force. The other reason that you can get rid of D is, if you added those forces together, you certainly wouldn't end up with a resultant force of 0, would you? So that's definitely not going to work. Okay, so we're left with A and C. Both of them look good because they've both got those 4 forces, and this is where we've got to come back to this idea that we want the resultant force to be 0. Why? Because it's in translational equilibrium, right? Okay, and A is going to be our best bet for that. Okay, if you look at C, the vertical forces balance. Oh no, they don't. Okay, that one vertically upwards, the buoyant force is going to be balanced by the weight, but then the vertical component of the tension, okay, is going to mean that the resultant force on this one will be downwards, right? So C is not the correct answer. Oh, elevator question. I love a good elevator question. Okay, so we've got the elevator accelerating upwards at 2 meters per second. Okay, and we're being asked to find the tension in the cable, right? Okay, so straight away we know that, okay, so what are the forces on here, right? We've got the tension in the cable, okay, and we've got the weight of the lift. How did I know that the tension vector force vector is greater than the weight force vector? Okay, it's because we know that it's accelerating upwards, right? So that means if there's an acceleration upwards, there must be a resultant force upwards as well, right? So from this, I can say that sigma F is just T minus W, okay? And then because I'm being asked to find the tension, then I can rearrange so that T is sigma F plus W. All right, I can work out the, this is MA, okay, and this is MG. Okay, so I'm going to substitute some numbers in. Okay, this is 2 times by, 800 times by 2. Okay, and this is going to be 800 times by 10. Okay, now I know that in the data booklet it says that actually G is 9.8. Okay, but quite often in the multiple choice questions, they kind of expect you to be able to do it without a calculator. I certainly know in the old exam specification you weren't allowed a calculator for paper 1, right? So a lot of the time they give it, you have to use G as 10, just to make the maths easy enough for you to be able to do in your head, right? Okay, so what have we got there? We've got 1,600, okay, plus 8,000. Okay, so the tension is 9,600 newtons, otherwise known as 9.6 kilonewtons. There we go, it's D.